This toy has fascinated me since childhood. To me, its motion is almost hypnotic. Here's how it operates. Wet the bird's beak thoroughly. Then stand it upright. It'll take a few seconds for it to start drinking. Notice that all the action right now takes place in the stem here. As I speed up the action, you see liquid rising and the bird rocking back and forth. If I return to normal speed, you can see the bird slowly, very, very slowly, rock forward until it takes a drink. The bird will continue this motion for hours. In this video, I'll detail the bird's clever engineering design, explain how it uses thermodynamics, and link its action to some of the greatest and most impactful devices created by engineers. This toy has a long history, but its current incarnation is due to Miles V. Sullivan, a scientist at Bell Labs. He specialized in methods of manufacturing semiconductors, but as a sideline invented toys. It's reported that this bird delighted U.S. President Herbert Hoover, an engineer who failed to figure out how it worked, and also defeated the great scientist Albert Einstein, who spent 3.5 months studying it. With the benefit of hindsight, let's start by exploring how it works and examining the key engineering design aspects. First, let's ask, is the water ornamental or essential? At first, the bird takes a drink, just as if there were water there. Now let's speed up the bird's motion. You see at 15 minutes, it's still drinking. 45 minutes still drinking. 75 minutes still drinking, and about 5 or 10 minutes later, so 80 or 85 minutes in, it takes its last drink, and while the liquid still rises a bit, it never rises enough to make the bird tip over again. So the water is essential. Let's test what it does by letting the bird drink this whiskey. Again, thoroughly wet the bird's beak with the liquid. Stand it upright. And then we see again the liquid rising in the bird. And then it drinks. Notice that the type of liquid affects the bird's operation. Compare the whiskey drinking to the water. Both have just dipped their beaks. Now watch. The whiskey drinking bird returns for a drink before the water drinking bird does, and it gets a second drink in before the water drinking bird does. I measured the rates and found that the whiskey drinking bird takes 3.66 drinks per minute, while the water drinking bird takes 2.33 drinks per minute. So the liquid is essential, well, at least kind of. Let's see what happens if I point a light at the base of the bird, which I've painted black so it will absorb the energy from the light better. As I heat the base of the bird, the liquid rises, as before, but the bird tips backward. The wet nose tilted the center of gravity, and so I added some modeling clay to the nose to get the bird to tilt forward. And then once the light's turned on, the liquid now rises. The bird drinks repeatedly, just as if there were liquid in front of it, until I turn the light off, and the bird drinks for a little bit longer, until eventually it comes to rest. Let's look inside the bird to get an idea of how the bird works. Underneath the bird's hat, beak, and fabric covering lies a glass bulb, smaller than the bulb at the base and also rounder. Now, watch as I put a few drops of isopropyl alcohol on the top bulb. The liquid rapidly rises to the head. This changes the bird's center of gravity so that it will tilt forward. The head now fills with liquid, and then there it drinks. It becomes upright and the liquid drains from the head. Liquid rises again to the head, and the bird drinks again. The cycle repeats until all of the isopropyl alcohol in the bird's head evaporates. Why does the liquid rise? The place to begin is with the bird's manufacture. The bird is filled through this tap with methylene chloride, which is then frozen, a vacuum applied to evacuate the air, the tap sealed, and of course later hidden by the bird's hat, and then the methylene chloride melts. It turns to liquid, and then some of it evaporates, turns into vapor. The methylene chloride will evaporate until the pressure inside the bird equals its vapor pressure at room temperature, a bit over a half of a typical room atmosphere. The key to the bird's operation is that the vapor in the head and in the base are separated by the liquid in the base. It's hard to see, but a tube extends into the base, nearly reaching the bottom. This separates the vapor in the base and the vapor in the tube and, of course, in the head. So at rest, the pressures in these two spaces are equal, but when the bird's beak is wet, the pressure in the head drops below that in the base, and the liquid rises. Of course, this liquid in the head causes the bird to tilt forward to drink, and when it drinks, the vapor in the head and the base are connected, and the pressures equalize, and the liquid drains from the head, and then the cycle repeats. To see the pressures equalize, I'll slow down the bird as I tilt it forward. Right now, the head is half full. When I tilt it, you see a bubble of vapor go from bottom to top. Notice that now the liquid in the head is below the top of the tube, and the liquid in the base is below the section of the tube that almost reaches the bottom of the bird. This allows the pressure to equalize, and as the bird becomes upright, the liquid returns to the base before the cycle starts again. Why, though, does the pressure in the head drop? You can see the answer if I shoot cool air across the bird's head. As the cool air strikes, you see liquid condensing inside the head. This causes the pressure to drop and the liquid to rise. You can understand this pressure drop from the ideal gas law. As cooling condenses the vapor, the number of moles of vapor, of course, decreases dramatically. The temperature decreases slightly. The volume at first stays the same, so that decrease in moles causes the pressure to decrease. I used to compress air to cool the head because I can control the amount of cooling. The bird, though, cools its head by drinking. The head is wrapped in fabric that absorbs water. As I put drops on the beak, you can see the water beads up at first, then saturates the fabric and spreads rapidly around the bird's face. On the right side, you can see it creeping to the back of the head. If I now turn the bird around, and you can see that the water has spread to the back. As I continue adding drops on the beak, the saturated area on the back increases. When this water evaporates into the air, it removes energy from the bulb as heat. This lowers the temperature and begins the condensation of the vapor, which starts the cycle as I showed you with the compressed air. As long as the head is wet, the bird will drink. Now, to make this condensation happen, when the temperature is lowered just slightly, the evaporating water lowers the temperature by only about 0.3 of a degree, the bird's designer chose a highly volatile liquid. This means one whose boiling point is near room temperature. Here's another toy that illustrates that volatile liquid. It's called a hand boiler and is also filled with methylene chloride. If I rested my hand, you see the liquid boils and shoots up the coils. We can now understand why the bird's rate of drinking differs among the three methods I use to activate the bird: a heat lamp, whiskey, and water. Roughly, the heat bird takes 3 drinks for every one of the water bird. The whiskey bird takes 2 for every drink of the water bird. The reason the bird drinks whiskey faster than water is because the rate of evaporation of the alcohol is greater than that of water. This means that heat is withdrawn faster from the head, and so more vapor condenses in a shorter amount of time, which accelerates the pressure difference. The heat lamp causes the greatest difference of all, which highlights how an engineer thinks about this bird. To an engineer, this bird is a heat engine. A heat engine turns heat differences into work, mechanical motion. To see that, recall that when the bird is just about to drink, that its head is at a lower temperature than its base, which is at room temperature. Then, when the bird drinks, the pressure in the head and base equalize, but the overall temperature of the bird is now just a little below room temperature. When it returns to upright, the base draws in energy as heat, the head then rejects some energy as heat, and the bird drinks again. These two flows define a heat engine, a device operating in a cycle that absorbs heat from a high-temperature reservoir, converts part of it into work, and rejects the remainder into a lower-temperature heat reservoir. The fact that this is a heat engine means it's related to the great machines that make our globalized world happen. Among those, the mighty steam turbine that generates electricity, the giant diesel engine that propels cargo ships across the sea, and the great gas turbine that flies us around the globe. I'm Bill Hammack, the Engineer Guy.